Hello everybody, welcome back. Today we're going to be starting 5.3, interpreting and sketching graphs. Today's focus will be how to describe a possible situation for a given graph and sketch a possible graph for a given situation. So we'll be going both ways. We'll be looking at a graph and we'll be describing it, and we'll be doing vice versa, having given a description and creating graphs. Let's make some connections. So in math, a graph can provide lots of information. The graph shows the depth of a scuba diver as a function of time. So again, that time is an independent variable, and the depth is dependent. So let's just answer a few of these questions here. It says, how many minutes did the dive last? Well, it started at 0, and it went to, these are going up by 2's, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. So the dive lasted approximately 30 minutes based on the information from the graph. Okay. At what times did the diver, stop her descent? So descent means continuing to go down. So you'll notice, and any of you have taken Science 10 already, you've looked at these when you've looked at position time graphs and displacement time graphs and distance time graphs. Okay. So when time continues but the depth doesn't, that's when the diver stopped her descent. So we say from 4 to 8 minutes, the diver did not go up or down in the water, and also from 10 to 14. 10 to 14 minutes. So those were the two intervals in which the diver did not go any lower. Okay? And the last one there, what was the greatest depth the diver reached, and for how many minutes was the diver at that depth? So you can clearly see that 20 is the 20 meters was the diver's greatest depth. And it says for how many minutes was the diver at that depth, and we talked about that before. It's right up here. So from 10 to 14 minutes, the diver was at that depth, so for 4 minutes, right? We would just subtract the 2. Okay. Let's look at some of the properties of a graph before we start the next example. So the properties of a graph can be provide information about a given situation. So here we have the scale for the dependent variable. So it's going up by 1. Sometimes you'll skip numbers, like you can put a 5 here and then a 10, or you can go by 2's, whatever. But each block is worth 1 unit. Same with here. The scale is 1. Okay. This is a steep increase. This is a steep decrease. There's no change here in distance. The time will continue, obviously. This is a moderate increase, a very steep decrease, and a moderate decrease. Okay. So let's interpret the following graph. So the following graph, each point in the graph represents a bag of popcorn. Sorry, a bag of popping popcorn. Explain the answer to each question below. Costs and masses of various bags of popcorn. So the first question, A, in example 1, says which bag is the most expensive? So if cost is here and it's increasing, obviously, we would go to the highest point located. Okay? And what does it cost? So which bag is most expensive and what does it cost? So we'll answer these questions. So bag C, you'd be correct in saying bag C is the most expensive because it is represented by the highest point on the graph, and the vertical axis represents cost, and that cost is $7. Or 6, so 1 up would be 7. So we go bag C, and it costs $7. Doesn't ask anything about the mass, so we don't have to. Which bag has the least mass? So, and what is that mass? So we go down here, we see B, and the mass is, well, if that's 400 and that's 600, it looks like it would be about approximately 500 grams. based on the data. So to write that in a complete sentence, when we're asked a question, it says bag B has the least mass because it's represented by the point on the graph farthest to the left, right? Because mass is going on the horizontal, right? So we grab the first point we see, first coordinate, and that mass appears to be 500, like I mentioned earlier. Which bags have the same mass? So that if they have the same mass, that'll mean they'll be on the same location, all right, on the x-axis. So right here, I think it's probably at 18. It's right on 1,800 grams, and that is bag D and E. They both have the mass of 18 grams. Different cost, but the same mass. So we see bags D and E have the same mass as I mentioned before, and that's because the points represent the line, the same vertical line, right? So right there, same vertically, same mass of 1,800. Okay, which bags cost the same? So it'd be the other way. We're going horizontal. A and E, they both cost $4. So bags A and E, like I mentioned before from the graph, they're both $4. So just to answer the question, bags A and E cost the same because the points that represent them lie on the same horizontal line, and it passes through 4 on the cost axis or the y-axis, which means the cost is $4. Which of the bags, C or D, has the better value? So this is more of an interesting question. You really got to do interpretation. So it says C or D. Which ones have the bigger value? Well, if you take a look, D cost probably $5.50 and you get 1,800 grams, but C is $7 and you only get 1,600. So obviously D, because of the lower cost and the higher mass, is a better bargain or has the better value. Okay, so bag D has a better value for the money because it has a greater mass than C and costs less than bag C. Okay. There's also a check your understanding question. It's the same idea. It has the ages and heights of people. You'll be asked a number of questions. The answers are here and at the bottom. Remember, don't look at those until you're finished. Cover them up prior to looking at those. That's just to make sure you have an understanding. Okay, let's look at this graph here. It says the graph shows how the volume of water in a watering can changes over time. Okay, so the starting volume is 1 liter, which is the volume of point A. And then segment A to B goes up to the right, so the volume of the water is increasing from 0 to 30 seconds. So I would assume you're adding more water to the watering can. From B to C, it hasn't changed. It remains at a volume of 1.75 liters. So it must have been just sitting there. No one's using it. All right. And then from 70 seconds down to 90 seconds, it goes down. So the volume is decreasing. So obviously someone is using and pouring the water out. That would be an interpretation of the given situation. Okay? Again, people can determine it, could have different answers here, right? Answers may vary. All right? So let's talk about this here. Trip to a day trip from Winnipeg to Winkler, Manitoba. So example 2, describe a possible situation for the graph. Describe the journey for each segment of this particular graph. And then there's a solution. All right. So O to A to B, B to C, C to D, D to E. So the graph and the journey, we're going to talk about those. So in the graph from O to A, we use O here for origin. Okay, that's a popular word to use when it's at 0, 0. Where the X and Y axes meet, or the vertical and horizontal, we call it O for origin. The graph goes up to the right, so as time increases, the distance from Winnipeg increases. In the first hour, the car leaves Winnipeg and travels approximately 65 kilometers towards Winkler, right? Because your driving distance is the distance between Winnipeg and Winkler, okay? In the second part of the graph from segment A to B, you'll notice that the time continues, but the distance hasn't changed. So the graph is horizontal. So at this time, as time continues, time will obviously is not going to stop, right? The distance stays the same. So you would say, so for approximately 15 minutes, because this is in hours, right? So that would be an hour, hour and a half. It's approximately in between. So the car has stopped for approximately 15 minutes. Might have had to go to the bathroom, might have had to fill up for gas, who knows, or a break. but the car is stopped. So a horizontal line of distance, time continues to increase. That means the vehicle is stopped. So the next part of the journey from B to C, similar to that from O to A, the graph goes up and to the right. So as time increases, the distance increases. So the car travels approximately 65 kilometers toward Winkler. Okay, or Winkler. I'm putting an R in there. Sorry, Winkler. My apologies. The next part we have obviously from C to D. You'll notice that the distance hasn't changed. You're at 130 kilometers, and it stays at 130 kilometers from between 2 and 4, so 2 hours. So at this point, I would assume we are now in Winkler, because now we notice that it goes back down from the next segment. So the graph is horizontal. So again, as time increases, the distance stays the same. So the car has traveled 130 kilometers. So it has reached Winkler, where it stops for 2 hours. So they spend 2 hours, approximately 2 hours in Winkler. All right. And then D to E is obviously the return trip. Looks like they haven't stopped. Went directly home because there's no stoppages at all. Okay. And we'll write that in. So from D to E, like I mentioned earlier, the graph goes down to the right. So as time increases, the distance decreases, which means they're coming back to return. So like I said, those of you who have taken Science 10, you've already had this part when you've done the physics unit in motion. So you're a step ahead. For those of you that have not gotten there yet, that's fine. The car travels and returns to Winnipeg, because O is the origin. That's Winnipeg. 130 is the distance, because it tells us this between Winnipeg and Winkler is 130. So there we have it. And then a completely straight drive home with no stops whatsoever. Okay. There is a similar question here. Again, it's check your understanding. They have some possible information at the bottom there for you for that. So you can try that as well on your own. Okay. So I'm going to stop there. In the next video, I'll finish up the section with the next examples. But thanks you everybody for watching, and we'll finish up. Like I said, we'll finish the 5.3 in the next video with example 3. Thanks everybody, and we'll talk again soon.